Our next speaker is Professor Sathish Vadhiyar, who is the chair of SCRC, the Supercomputing Education Research Center, and also a professor in Center for Data Sciences here at IISc. He'll be talking about MPI, and he'll be giving an MPI tutorial. So MPI is quite relevant for us because we use MPI for parallel animation. That's why it gets our. So this is do the full screen. Yeah, slideshow. Yes. Yes. So once again, my name is Sathish Vadhiyar. Sorry, I should have talked that. So as somebody mentioned, so I'm associated with both Computational and Data Science Department as well as the SCRC, which is for Computer Center. So when you get time as part of this workshop, so please do work SCRC and look at the I think right. So the most powerful supercomputer in an Indian academic setting. Right. So, and one of the ways you can program such large machines, right, so and even having multiple nodes is MPI, which is what right. So before I go forward, so thanks for this opportunity. So if OpenMP coverage is going to cover, ideally will take a few lecture hours, right? So MPI is going to take much more than that to give a proper view. So sometimes it so it can take close to it's about 1.5 hour lectures, but the great thing about MPI is that there are these common small set of functions that you can cover quickly, right? So and then start becoming an MPI programmer right away, right? So I'm not going to cover about how to compile and execute MPI programs, which you can learn from the online resources. And one of the online resources was mentioning earlier. One of the great resources, just search Google for MPI complete trends. Okay, so there is so it's not a separate language by itself, right? So if you have C or Fortran programs, you need to insert few statements, few header files, and there is a particular way of compiling your MPI programs. If you are using GCC, for example, or CC, you will instead be using MPI CC. And then there is a particular way of executing where you specify the number of processes, MPI processes to spawn, right? So now those processes stay forever under right. So under MPI 1, right? So there are several versions: MPI 1, 2, 3, right? So and then I guess subsequently MPI 4, right? So has also may have come up. So the normal practice is when you execute a program by specifying in the command line, you can specify the number of processes with which you want to spawn, and you can also specify the host on which you want to spawn the processes. Those processes stay throughout the lifetime of the program. Okay? So that is where OpenMP slightly wins over MPI. Within a program in OpenMP, you can change the number of threads, right? So the amount of parallelism, whereas here, right? So it's a bit of static parallelism in terms of the number of processes. Although in MPI 2, they did introduce dynamically spawning processes in the middle of the execution. didn't quite take off because of various reasons. So with that, now what is MPI? MPI relies on the concept of message passing. So Professor Govindarajan talked about shared memory parallelism. Within a node, right? So if you have multiple cores, there is this concept of shared memory. You have these multiple threads executing on these cores, then all threads are executing a single program. So the threads kind of communicate with each other through via this shared memory, right? So if one thread writes a variable X, right, and another thread, right, so at a later point of time reads the variable X and proceeds, right? So all parallelly performing different parts of the same program. So they can't be completely parallel. There has to be some exchange of data. So in shared memory parallelism, this exchange happens through the shared data in the shared memory. Whereas MPI is primarily meant for distributed memory programming, where if you have multiple nodes, right? So let's say your laptop and my laptop, right? So we want to combine to form a quick parallel processing platform, right? So obviously the memories on our laptops, right? So they are not shared, right? So then how is the X that is written by your process on your laptop can be accessed by my process executing on my laptop? So the only way is to pass that variable X as a message between the laptops, right? So this is the concept of message passing parallel programs, which are ideally suited for distributed memory. The reason we call it as distributed memory is both the laptop's memories, right? So they're not shared, they're distributed, right? So now imagine, so this is just a quick two parallel processor platform. The one that you see will be seeing in SELC when you get has about 28,000 cores. Now, the largest systems in the world, right? So I would suggest you go to top500.org website, right? So they have close to 2 power 20 cores or 2 power 25 cores, right? And why? Because there is a real need for such parallelism for various applications, right? So and definitely astrophysics is one application which is greedy for more and more resources, right? So and when you have such large number of cores, it is not possible to have all of them in a single gigantic shared memory paradigm. You cannot have a huge shared memory that can be accessed by all the cores, right? So there's going to be lots of hardware constraints related to that. The only way is putting together distributed set of nodes of a cluster into a parallel machine. Right? So and when that happens, you can only use message passing to parallelize the board. So it's MPI is widely used as a de facto standard for distributed memory programming, right? So here more control is with the programmer. You explicitly add message passing statements within your code. So the important thing is it is a standard. Okay, so it is not a particular implementation. So the MPI forum, right, which started in 1992, right, so came up with the first standard in 1993, and MPI 2 in 1997, MPI 3 in 2012, and subsequently, right, so any other MPI versions. What this forum does is to come up with standards related to message passing programming, right? So if you want to have a point-to-point communication, right? So for example, something that has received what should that send call be? What that receive call should be, right? So if he wants to broadcast the text to all of our laptops, right? So what should the broadcast call be like, right? And then this standard in turn is implemented by different MPI libraries on various platforms, fine-tuned to the platform. So we'll have to quickly differentiate between standard and implementation. MPI it's not the term MPI is not a language by itself. It specifies a standard, and different implementations and different libraries implement that standard, right? And the reason why that standard was felt was prior to that, different platforms were following their own ways of communicating. So when you write a program for a particular platform, right, and then you want to migrate your program to some other platform, you will have to kind of rewrite many of the communication calls because each platform was following its own communication paradigms. So MPI, that is when MPI Forum stepped in to come up with a standard, right? So that's so much for introduction. Now, what does this MPI contain? As I said, it contains standard for point-to-point communications between two processes, right? So electric communication, I was giving the example for broadcast. It helps in creating communicator groups, right? And associated communication contexts. Okay, we'll see about that. It also helps in creating process topologies. Right, so what that means is that how the processes should be communicating with each other. Should they be following a linear pattern where one process sends it to its left and right neighbor? Should they follow a 2D mesh-like pattern where there are these north, south, east, and west neighbors, and so on? Right, so and then subsequently in right, so for now, let's ignore this. So subsequently in MPI Standard 2, there was this important concept of MPI IO, and then dynamically creating processes that I was mentioning above. One-sided communications, where, right, so in the MPI 1 standard, you need two processes for communication, right? So, but there are various non-deterministic programs, right? So where a process just creates some value and then right, so and then puts it into some other memory, right? So some other process memory, right? So hoping that that process may need it some other time, right? So as you can see, there's a lot of non-determinism even in the definition. So this kind of paradigm has become really important in the modern day large-scale exascale systems where you don't want to tie up a pair or a group of processes come to any kind of synchronization point, right? So the processes just keep going, right? So whenever they try to produce, right? So they just dump into some other memory and they keep carrying on, right? So what we'll be covering in the next, right? Supposed to 40 minutes, and so Pratik just took out my words, so I wanted to begin by saying I'm going to give a whirlwind tour, right? So that is what this is going to be. So we'll be covering point-to-point communications, telephony communications. We'll also delve a little bit on groups as well as this process topologies, right? So with that, you will be kind of ready to right. So remember these concepts, right? And even start writing significant programs, right? So, but there are other important things that I would encourage you to highly look at, right? So, MPI parallel IO is very important, right? As well as I said, one-sided communications has become more and more important in the modern day large-scale systems, right? So let's start looking at point-to-point communications. So this is how point-to-point communications look like. One of the processes called sender process calls a function called MPI send, passing to the program, passing to this function a buffer that has to be sent, and then some characteristics of the data that has to be sent, right? So that is, what is the total number of elements in the buffer, what is the data type in the buffer, right? So and then all of this is sent to what is called as a right, so to a destination process. Now, how do we identify a destination process? Just like in OpenMP, you have this OpenMP thread ID. In MPI, each process gets an ID. In the context of MPI, we call these identifier as track. Okay, So when you start your program, let's say with 8 processes, each of the processes is given rank starting from 0, right? So one process will have rank 0, next another will have rank 1, 2, 3, etc. Okay? So that rank of the destination process has to be specified in the sender process. And each right, so the communication also this message that is being sent can also be given an ID, right? So not so as to kind of create context for the different messages that may be sent between the same pair of processes. So that message ID we generally call as message tag. And the important thing here is this last argument called communicator. Right. So what a communicator is, it is a pointer to a particular process. Right. So pointer for a particular process pointing to a communication group. Right. So that is created. Okay. This communication group has a set of processes. Okay. So when you initially when you start with a certain number of processes, the processes, right? So I was giving this example of 8 processes, right? So all of these 8 processes will come in a single communication group. Okay. So and then each process now will need some handle or a pointer to this communication group, right? So that handle, right? So our pointer is what we call as communicator. Right? So this is a very important concept in MPI. Almost all the MPI functions will use this communicator. Okay, so this right. So if you want to be just right, so clear about it, you just think of it as some variable that represents a communication code. Okay, so we will see some examples where things will get even clearer. Now, this message that is being sent by the sender will have to be received by another process called the receiver, which receives that message into its array, and then the receiver process should also specify the parameters of this message, the number of elements and the data type. Now it has to specify the source rank, right? So from what process it is receiving this message, and then it also has to specify the same message ID, so that right, so the corresponding message is received, and right, so it also has a variable which should point to the same communicator group. Okay, and finally, right, so there is this one extra argument in receive which is called as a status argument. Using the status argument, you can query, right, so what happened to the message, right? So there are a number of querying functions. One of the querying function functions as an example is this MPI get count, right? So which you can query on the status to find out what is the actual message size that this receiver process received, right? So as simple as that. Now, there is also some association between the ranks and the communicator that is specific, right? Now, each of us, right, so can have multiple IDs, right? So multiple ID numbers, right? So imagine each of us has a process, right? With respect to IISc, right, so I have a particular ID number. With respect to some other institutions that I've been in, right, so or some of the active groups that I may be involved in, I may be having different ID numbers, right? So it's not only enough, right? So for you to reach out to me to right, so to say to just give the ID number, but you will have to give also the context, right? So the ID number with respect to ID, with respect to IISc, the ID number with respect to some other active group, right? So that is this plan, right? So this specifies the ID number, but that alone is not enough, because single process can belong to multiple groups, and in each group its rank can be different, right? So its ID can be different. So you also need to specify the group, right? So and that specified using a particular communicator handle. So, as I've been trying to insist, it's not any esoteric language, right? So, based on the experience in my class, I can say, right? So, within a couple of weeks, right? So, you can really start writing some reasonable parallel programs, right? So, the learning curve is not any steep, right? So, or anything. So, this is how simple it would look, right? So, within your C or Fortran program, this I guess assumes some kind of C semantics, right? So, so you specify a communicator, right? Now, one important communicator that you will have to remember, right? So, is this wild card called MPI com word, right? Now, MPI com word represents the group that contains all the processes. Okay, so now from this group you can form subgroups, and for each of those subgroups you need to have another communicator, right? So we will come to that at a later point of time. Hopefully the time will permit, right? So, but the default group, right? So containing all the processes with which you start the parallel program, that group is represented by this communicator, right? So represented by this what we call as white card called MPI convert. So now this communicator represents the overall group of all the processes, right? So and then now there are some querying functions, right? So using this communicator, for example, this executing process can query what is its own ID, okay? And now, having known that, just imagine this is a two-process program, right? So now the first process may be initializing this array, and then right, so after the array initialization, it keeps half of the array to itself, whereas it sends from the second half, right? So if there are a total of n elements in the array, n is the starting point, right? So plus n by 2. It sends the second half of the array. Now it says n by 2 elements of type integer. Okay, and this is the message ID, right? So, sorry, this is the rank of the destination process. So process 0 is trying to send the process 1 with respect to this overall group of all the processes. Okay, and it can specify some message tag, any integer like 5 or 10 or whatever. Now this message is now received into this array B by the second process. Okay, and after then both of these processes can independently proceed with respect to their right, so independent arrays, right? So this is right. So this is how simple it can get. Okay, but we'll see more realistic examples as we go along, right? So for now, hold on to any doubts you may be having. So as I was saying, right, in MPI, every communication has a scope, right? So or a context. The context is defined by the group and the communicator and the rank within a group to which you set, right? So likewise, the message also has a context where we give the message ID, okay? And this communication pointer to a group is what we call as communicator. Yeah, and I had already shown in the example that the default communicator is MPI convert. The communicators can be either inter or intra communicator. Very quickly, what it means, right? So at this point, is you can create a group and you can create several subgroups, right? So multiple groups. Okay. Any communication that happens within a through a communicator, right? So we call that as intra communication, and the communicator is used for the purpose is called intra communicator. And let's say sporadically you want to communicate between processes of two different groups. Okay, so you then create what is called as an intercommunicator that can only be used to communicate between the processes of two different groups. Okay, so and that is the concept of intra and intercommunicator. So we will look at it right so as we go along. other important utility functions is you start your program by calling this MPI init function, and when you into your program using MPI finalize function, this sets up the MPI environment within your program. So the region within MPI init and MPI finalize is the MPI environment created in your. So we had already there are some important querying functions using this communicator, and for now let's worry only about that MPI COM word. You can know the total number of processes in that group. That is right. So that is pointed by the MPI COM word or any other communicator. And we had already seen in that small example that a process can also query its own rank. Okay. So here is almost a workable example. I'm not sure how visible it is at the back, but I'll try to walk you through. So here, let's say you're trying to use two processes, and you have this large array, right? So, and you're trying to you're dividing the array into two parts across these two processes, and you want both of the processes to find a global maximum in this array. Okay, and you just let both of these processes go. They find the local maximums with respect to the local arrays. And finally, you want to make use of this to find the global maximum. Okay.
So, can you just say that, can the audience be on mute, please?
Can the audience please be on mute? I see. So you can start within your main program by including this MPI.h in the file, right? So there is this MPI program, right? And there is this overall global array, and then there is this local array. Okay, you start your program with MPI init, okay, and you're going to use this MPI COM world communicator. You use the two querying functions. That's a go here. MPI COM underscore size and MPI COM underscore rank to find out the total number of processes that you have started your program with, and the rank of this particular process that is executing the program. Now this is right. So I think in the earlier lectures you may have come across what is called as an SPMD program, single program multiple data. This is a classic example of that, right? So the same, what it means is it's the same single program that is executed by multiple processes, right? So, but they're all working on different parts of the data, right? So what it means is that when you start this program with two processes, and then you print this rank, okay, somewhere here, then one of the processes will print the rank as 0, and another process will print the rank as 1, right? So they just right, you get two different IDs. Now, so just to ensure, right? So this is how the size can be used, right? So just to ensure that this program works with only two processes, and you cannot start this program with more than that, right? So you check on this size parameter, right? So if it's not 2, you just abort. Okay, and so then now you are ready to read the data. So the process 0, let us rank equals 0. It reads, right, so the total number of elements of the array, and sends that count, right, small to process 1, right, so which receives it. Then, right, so then it does some dynamic allocation of the array A, and then initializes the array, right? So those things have, right, so can happen somewhere here. So now it copies, right? So it creates a local process 0 creates a local array with the first half of the data, and sends the second half of the data to process 1, right? So which receives it into its local array. Now at the end of this if and else condition, both of the processes refer to this variable called local array, right? So but containing different parts of the data, right? So for process 0 it is the first half. For process 1, it is the second half, right? So now both of the processes, as you can see, right? So this is a common section, right? Now both of the processes will be checking for the right. So the maximum within that local array. Okay, and we ultimately want in this program want process 0 to print the global max. So the second process will send its local local maximum to process 0. Process 0 in turn receives that maximum that is received by from process 1 and compares with its own maximum that it has found out of its local array, and based on that it finds out what the global maximum is. Finally, that global maximum is printed. Right. So this is almost right. So a compilable and executable program you can write out. Right. So this is as easy as your program can get. Now, even in this program, it may look like we are adding lots of if conditions, MPI statements when compared to sequential maximum finding. That's because the program is small, right? So in a really large code like Pluto, right? So you wouldn't even see, right? So less than, right? So more than 15% of the code occupied by these MPI statements, right? So these conditionals, right? So right, so that is the advantage of MPI. So maybe I'll stop here a little bit because it's important going forward. So are we clear with this example? Yes.
The printf is outside the if. So
yeah, you will see two printfs in this case. Yeah, correct. Any other questions? Okay, so let's assume that the simple example is clear to everyone. So let's move forward. Right, so that is send and receive that we have seen till now are called blocking send and receive. MPI also supports another important kind of communication paradigm, point-to-point communication called non-blocking communication. Okay, so the popular analogy that I keep giving every time I cover this is right. So let's say that we are going to right. So we are going to a fast food counter. Right, so and then we are ordering something, right, and then right, so we order something and then we get a token, let's say for a dosa, right, so and then we go to the food preparation counter, right, so give this token, right, so and then if you notice, right, so they will give one token to you, right, so back. So now, right, so you can come back, and while the food is prepared, you can do something that is not dependent on the food preparation, right? Like for example, at the time you can fiddle around with your phone messages, or you can speak with your friends, right? So then, right? So you go back to the food counter, right? So and then you read your token, show your token, and then see if the food is completed or not, right? So okay, and you can repeat this multiple times. You can wait or right, and say you're done with everything else outside the world, right? So in the world, right? So other than this, in which case you go to the food counter, right? So you keep waiting for it, right? So that analogy to the point-to-point communication, right? So there is this communication going on between send and right? So between sending process and the receiving process. Okay, so in sometimes when the message is really large, it can take right. So this. Especially this receiver, right? So have to, and we also don't know when the sender is going to send, right? So the receiver may have to its receive point much earlier, right? So and then it basically, if you use a blocking receive, right? So it keeps blocking for the communication to come, right? Instead, right? So if you use what is called as the non-blocking communication, you right? So where you post a special kind of receive, and you get a token back, right? So this token is called as a request token. Okay, and then you can now within your program you can do something that is right highly independent of this communication that you're going to receive, right? So you can do some other computations, right? So which does not depend on this message that is being received. In other words, you can overlap the communication that is happening with some useful computations, right? So this non-blocking receive is highly useful for that to overlap computation and communication, right? So and then at some point you need to see, right? So whether the message has arrived and whether, right? So you want to complete it. So remember that those are counter example, right? So this token you call another function, right? You call right? So there are two functions, right? So MPI test to see if the communication has arrived, right? So and you get that indication in this Boolean flag. Right? So if it has not arrived, then maybe you can execute some more non-dependent statements, right? So and then you go back. MPI test, right? So as you know, those are arrived, right? So MPI test, yes, right? So and finally I'm done with everything. So right, so I'm going to wait, right? So till I get the dosa, right? So and finish this communication. Okay, so it's the same as you can see. Most of the parameters for this non-blocking send, now we are going to prefix it with I to differentiate the blocking and the non-blocking sends. Right. So for the non-blocking sends and the receives, there's this one extra parameter called this request. Right. So of type MPI underscore request. Right. So which is that token. Now with that token, you can later query for the completion of the message and finally wait, right, so to fully complete the message. Okay, so it's a highly powerful mechanism for doing point-to-point communication. So when in doubt, it's right, so it's always safe to convert your point-to-point communications to non-blocking communications, and many people have seen vast improvement in performance by doing that.
So this wait and test runs on all processes, both processes, the sending and the receiving.
Right, so that's a good point. Yeah. So this is right. So this is a sender process. So this is the receiver process, right? So you can mix and match blocking and blocking, right? So these are highly independent, right? So for example, you can call a non-blocking send on the sender process and a blocking receiver the receiver process, right? So you can right, so or vice versa, or you can call both, or you can call non-blocking sends and receives in both the sender and receive process, right? So this wait, right? So this non-blocking send, right? So and the corresponding wait and test are completely local to a particular process, right? So likewise, the non-blocking receive and the corresponding wait and test are completely local and independent. That's happening in the receiver process. Okay. Right. So we have already seen this. Right. So now here is a now when would non-blocking right, so send and receive be useful? As I said, right. So for overlapping computation and communication, that is definitely one of the reason why people use non-blocking communications. So there is also there are also cases where your application throws non-determinism, right? So and when you don't know exactly when someone is going to post a send or not, it's highly unsafe for you to post a blocking receive, right? So because that message may never come, right? So instead, you want to make it non-blocking. So here is an example. Right, so I'll quickly right, so go over this. So let's say that you have a global array that is distributed across both the processes, and for now, let's imagine that all the elements in the array are unique. Okay, and you are trying to find a particular element in the array, right? So which the user gives us in. Okay, and that element may either be in the part of the array that is held by process 0, part of the array that is held by process 1. Okay, so so here, so in these statements, you initialize this variable called the other rank, right? So that is my rank, right? So and the other rank. At the very beginning, you post a non-blocking receive, right? So that to receive the index, right? So from the index of the array held by other process, if that part of the array is going to contain this element, okay? So and you're going to do this, right? So imagine if you had instead post the blocking receive, then you are assuming that the other process definitely has it, right? So and you will never move forward. Okay, whereas here you want to move forward, right? So by anticipating, right, so that someone else, the other process may have that element. Now both the process, right, so they both go ahead and try and right, so search for this element in the respective local arrays. Okay, if the element is found in one of the processes, then that process sends the index to the other process. Okay, and right, so and they both compute the global position. And if the element is right, so is in fact found by this process, then definitely that element is not going to be found by the other process, because the elements are going to be unique. In which case, right, so you can make use of this cancel function to cancel this non-blocking receive that you have posted, right? So because you have posted that non-blocking receive, assuming that maybe the other process has it and it's going to send it, but you have found it, right? So hence you can cancel that request, right? So and this completes the program where, right, so let me just make this right. The element is not found, right? So then by this process, then you are going to check if the other process has found it or not, right? So by doing this test, right? So if the other process has found it, right? So which this test will tell you, you are going to complete it, right? So and then you're going to break out of it, right? So as you can see, this is right, so highly non-deterministic. You don't know, right, so which process is going to find it and at which position in the array, right? So, right, so it's highly useful to have non-blocking kind of communications in this particular case, right? So, any quick questions before we move on to the next section, collectives?
Why did you have to wait?
Right. So this is one common mistake that many of right, so my own students do, right? So it is a safe way of programming to complete the communication using MPI way, right? So because we never know what happens in the MPI implementation, and the MPI wait function is supposed to completely clean up, right? So any allegation, whereas this will just tell you if the communication has failed or not, right? So any non-blocking communication, it's always safe to complete it using wait.
Is there much overhead to it?
In wait, if the message has already arrived, then it's going to be a completely local operation. So, right, so that will not be concerned with
But I think I'll ask later.
Okay, fine. So now let's move to the next section. So collective communications. So how much more time can I take?
You can take 10.
Okay, sure. Right. Right. So let me go over it quickly. Okay. So there is now all those communications that we saw involved processes, right? So now let's say, what if we want multiple processes to be involved, right? So and why do we want multiple processes to be involved in a single communication? Here's an example, right? So the classic matrix vector multiplication, where let's say you have divided the matrices and vectors across the processes in row decomposition, which means the first set of rows will be given to process 0, the second set of rows will be given to process 1, third set of rows to process 2, and so on. So now what we want to do is, right, so for this process 0, let's say if it's working on the first row, it wants to multiply that first row with this entire B, right? So but this entire B is not contained in it, right? So that B is already distributed across the processes. So you want all the processes to send their parts of B to this process 0 and process 0 to collect it, right? So you can do all of that using point-to-point communications by having this loop, right? So where the particular process 0, okay, inner loop, right? So we'll keep receiving from different ranks, right? So and keep accumulating that B, right? So likewise, using if conditionals, you can say if I am another process, I'm going to send my part of B to process 0, right? So all this, right? So we'll introduce at least 7 to 8 statements in your program, right? And right, so the more the statements, more the conditionals in your program, the more error prone your program can get. Right, so all of this is simplified by a single collective communication, right? So called all gather, right? So what this all gather does, right? So is all of the processes now instead will just be calling all gather. So as the name suggests, this data that is spread out in all the processes will be gathered in all the processes, right? So hence the name all gather, right? So this is right. So this is one motivating example. So here I have given, right, so how you can go about doing this, right? So now imagine instead you have divided the processes column wise, and you want, right, so and P and X are anyway vectors, you will have to divide it, right, so right, so across these plots. So now let's imagine now process 0, so the first row has to be multiplied with this P. This first row is distributed, it's not in a single process, right? So what you, right, so let's say what you want to do, right, so is you want each of this process to compute their local dot product, right, and ultimately then add all of them to finally find out this X, okay? So hence this initial local dot product calculation is an entirely local computation, but then what you want to now do is these local contributions of the local dot products by all the processes, you want to add all of them up, right, and store it in a single process, right? So that can be done using a very right, so using a simple collective operation called MPI reduce, right? So what it does is if there are these arrays, right, so spread across multiple processes, and you want to add up all of them into a single contribution, right? So in a single process, right? So you can make use of MPI reduce. In addition, MPI also supports MPI max, right? So if let's say you want to find out the max of the elements spread out across the process or the min, not only that, you can introduce your own user level functions, right? So because addition, max, min, right? So they're all functions, right? So you can introduce your own functions to do to specify what to do with these local contributions, right? If you want the result to be spread across all the processes, then you use what is called as all reduce, right? So likewise, there is a scatter operation to scatter the data that is there in a single process across the multiple processes, right? So and you want, if you want to gather the data that is already distributed in multiple processes into a single process, you use what is called as gather, right? So here is how we can, right? So these statements say how to proceed with the column, right? Column-based decomposition for that matter. So mostly these collective communications, right? So they're very interesting to program as well as to implement. There are these different kinds, one to all. For example, the scatter operation on the broadcast operation is an all to all operation. All to one, this gather operation is all to one, and all gather, right? So and there is also another function called all to all, right? So this involves communication and sending and receiving by multiple processes, right? So it's in the category of all to all communications. In addition, there is a primitive function collective communication which is very important called MPI barrier. There are in many of these numerical codes, right, that are iterative, you want all the processes to synchronize at the end of the iteration before they all can move to the next iteration. The way you can achieve that is by calling this MPI barrier at the end of this iteration. So that, right, so only those, when a process calls this MPI barrier and comes out of, right, so it can be reasonably sure that the other processes have called their barriers, right? So that is the synchronization that this barrier call achieves, right? So and then we had already talked about MPI broadcast. If there is a single message that has to be broadcasted, right? So there is this all-to-all communication, right? So where each process, right? So this is the process dimension, right? So each process has some unique data that it has to send to every other process, right? So in those cases, we use this all-to-all communication.
So the right representation is a single process.
No, the right representation is also this, right? So this is the row dimension is the process and the column dimension is the data. The right representation also represents the same. That is what happens after all-to-all. This is the input of all-to-all and this is the output of all-to-all. So for example, process 0 has A3, right? So that it wants to send to process 3. After all-to-all, that A3 would go to this process 3 and will be stored in the as the first element. Okay. So there is also reduce, scatter, and scan, right? So in the interest of time, let's not go over it, right? So these are different variations of the reduced operations. Okay, so these are the collective communications, right? So there are two other sections I'll just, right? So, run through them, right? So in less than 5 minutes. So that is, all of this involves, right? So start staying with the same number of processes and the same group of all the processes that you started your program with by using MPI Convert, right? I'm sure, right? So in large scale applications like Pluto, right? So where let's say multiple teams may be involved, right? So and each of the team works on a particular module, which is a parallel program by itself, right? So you have these different self-contained parallel modules, right? So and you want to bring them all together in a single coherent parallel application involving communications between these different groups, right? So that is when, right? So you need to be able to form groups, and you need to be able to form this intercommunicator for communication between the groups, as well as for communication within the groups. So, so as I said, right, so there are these two kinds of communicators, intra and inter. One way to form a group out of the existing set of processes, right? So it's using this function called MPI split, right? So what happens is all of the processes will that belong to this group represented by this input communicator will be calling this function with their own color and key values. These are integer values, and based on the color and the key values, now they all will belong to different groups that is represented by the new communicator. As an example here, for example, right, so rank, right, so 0, right, so 3, 5, and 6, right, so they're all called this MPI com split, right, so with color value 0, okay, now which means that all of them will now belong to, right, so belong to the single group, right, so at the end of it, and within that, right, so they need to get their ranks, right, so on that rank is determined by this key value, right, so the lower key value of process, right, so the person that has called this MPI split with the lower key value will get the first rank, right, so the next lower key value will get its second rank and so on. So just using the single function, right, so and with this example, right, so now they all have, right, so formed different groups. Yes.
So there are key values which are similar, or F and G, and how to determine the unique mix states.
Yeah, right. Very good. Right. So very good quick observation in that. As to the types of broken orbital. They are broken. Right. So in case of time, right. So they are basically broken orbitally. Right. Yeah. Depending on the MPI interaction. So good observation. Right. So now having formed these intercommunicators, you can now form right. So what are called right. Right. So you can now form what are called as this intercommunicator, where right. So you form these groups. My typical example that I usually give for this kind of example is climate modeling, right? So where in a climate system model there is there is an actual code that uses these principles, right? So there is ocean modeling, right? So there is atmosphere modeling, land modeling, right? So when it comes to climate modeling, each of this is a separate field by itself, right? So even in our climate modeling department, there are experts working just on ocean modeling, experts working just on atmospheric modeling. But then your overall climate modeling depends on all of these individual processes, right? So each of this, right? So you form groups of processes that does just the atmosphere modeling, groups of processes that does right? So only the ocean modeling. But then they're not independent, right? Like in real life, right? So what happens in the ocean is going to impact the atmosphere and vice versa. So there has to be some sporadic communications between these two groups, right? So in that case, you form these local groups, local communicator, and you use this function called inter-communicator, where there is this concept where each group specifies its local leader, and then specify a bridge communicator, which is a common communicator that connects them. In the first case, you can also always specify MPI called as a common communicator. And then you specify the remote leader, and you get this inter-communicator. So here is a quick example. I'm not going to go over that. So basically, all these 12 processes using this MPI split are split into 3 different groups, and then you use this intercom create function in each of these processes to do this kind of right to neighbor group communication. So the last couple of minutes on this very important topic, right? So many of the numerical simulations, right? So they don't they don't necessarily have this need for any process to communicate with any process. There is always right. So most of the time, the domain is divided into grids, right? So and there is going to be only interactions between the neighboring processes because the elements only depend on only the neighboring elements, right? So whereas if you use MPI convert, you are telling MPI that any process can communicate with any other process, right? Sometimes it is good to structure your code where you specify what communication pattern you're following. Are you following near-neighbor communication along a single dimension, in 2 dimensions, 3 dimensions, etc. So specifying this will basically improve the readability of the program. And from the computer science point of view, it can also help improve the performance of the MPI implementation when you do that, right? But the second aspect, let's ignore for now, right? And definitely helps improve the readability of the program. One of the common, so that is called as process topology. That is, you are arranging the processes in a particular topology, right? Either as a linear neighbor-based communications, right, or a 2D neighbor-based communications, etc. So that aspect is called process topologies. And one of the common topology is this Cartesian topology, right? So having these Cartesian coordinates in single dimension, 2 dimension, 3 dimensions, etc. So you can right, so all of the processes can form this Cartesian right, so form this Cartesian topology into what's called as a Cartesian communicator, okay, which you can create by using this Cartesian create, right? So here all of the process, this is a collective call by all the processes that belong to this group pointed to by this communicator, and you specify the number of dimensions in this Cartesian communicator, whether it is single dimension, 2 dimension, 3 dimension, multiple dimensions, etc. And you also specify the number of processes in this dimension. So what it means is right. So I was giving this example of 8 processes, right? So you can now arrange these 8 processes as 4 cross 2, right? So what that means is if you have a 2-dimensional domain, right? So you can divide the right. So the domain as right. So 2 cross 3 processes. So you know right. So specific blocks of this domain get assigned to a particular process. Simply that, right? So that block, right? So it's going to depend only on the neighboring blocks, right? So not far away blocks, right? So this really improves the readability of the program. Once you do that, then you can make use of this shift function, right? So using this Cartesian communicator that was created to find out the neighboring process. Thereafter, right? So you can, using this shift function, you can find out what is the source process and the destination process in each of the directions, right? So I have, right, so due to the paucity of time, let me not go over this, right, so but I have sent the slides, right, so this is one practical example, right, so Cannon matrix multiplication is one of the popular parallel matrix multiplication, which relies on forming this process topology. As the arrow shows, right, so you will see that, right, so there is always going to be communication only along certain specific row or columns of process, right? So it's not that any process, right, so will require, right, so data from any other process. So hence, because of this structure, right, that is involved in the computation itself, it's good to have that structure in your MPI program by creating this Cartesian communicators. When you do that, right, so then, right, so as you can see, you create this Cartesian communicator, right, so and then, right, so you communicate only with the right, so left and right neighbors, right, so that's what this program is for. So with this, I'll stop here. Sorry, I've already taken a few minutes. Thank you. Any questions? I'll be having to take questions.
I just wanted to clarify, so these instructions are processed by the CPU.
Yes, right. So API program runs only on the CPU, right? But what we all should be targeting as systems are getting more and more heterogeneous, involving GPUs as well, right? So you have a single node with multiple cores, right? So and the GPU card attached. Now imagine multiple nodes, right? So between the nodes, the only possibility to do parallel programming is MPI, right? So and within a node on the CPU side, we can have OpenMP because memory is shared between the multiple cores, right? So and on top of that, you can offload some of the computations to the GPU, right? So you will in many of the modern day programs, you will see such hybrid programming involving MPI, OpenMP, and more.
I have a question.
Yeah. So is it not possible to communicate between two different nodes of GPUs directly?
From one GPU to another GPU, yes, right. So there is something called GPU aware MPI, right? So where so when you compile your MPI program, right? So along or GPU aware, CUDA aware MPI, right? So for that, when you compile your MPI CUDA program with specific flags, right? So you will be using MPI, you will be able to initiate direct communications between one GPU to the other, right? So just search for CUDA aware.
Yeah. So at least the two examples that we looked at, the good examples, they don't have more if-else statements. And in the first lecture, we were told that GPUs generally don't do well with if-else statements. So that's
right. So all of these are running on CPUs.
No, the CUDA aware API.
Right. No, in the CUDA aware API, that is just for enabling pulling data from GPU on one to right, so on, right. Many MPI statements you have will be executed only on the CPUs of the respective.
Yeah.
Other questions? Let's start the straight questions. I'll take order for lunch at the same pace. So they will join us, right? Maybe this was soon. Okay. Sure.